Hello, good evening, everyone. I hope everyone is doing well, everyone is safe. So, this is the part 4 of the self-supervised learning. So, previously we discussed different ways of doing self-supervised learning, and in this video, we are going to discuss one such simple method called rotation net. And basically, it comes from the paper Unsupervised Representation Learning by Predicting Image Rotation. It's coming from Spyros Gidaris, Praveer Singh, Nikos Komodakis. So let's see what this paper is about. And this paper was published in ICLR 2018. And in the abstract, they have mentioned that by doing this kind of self-supervised or unsupervised pre-training on LXNet, they were able to achieve state-of-the-art performance of around 54.4%, which was only 2.4% less than the supervised case in case of the Pascal VOC 2007 detection task. And they also show that by transferring the learned features using this unsupervised learning method, they were getting very good results compared to the supervised and other unsupervised methods. And they did it for various tasks like classification, segmentation, and detection. So let's see in detail what the results are, what the method is, and what the authors have put in the paper. So the idea is very simple. I think from the name itself, predicting learning features by predicting rotation, it's very clear that what the authors are doing in order to learn in unsupervised way is that they have the image and they rotate the image. So they're doing it by multiplying by a factor of 90 degrees. So 0, 90, 180, and 270. And the network is tasked to predict the degree of rotation. So in essence, it becomes a simple four-way image classification task. But here we are doing it in a unsupervised way, means we are not using the actual labels of the data, but just we are creating the proxy labels, and those proxy labels come from this geometric transformation of rotation. So that's the whole idea of this, paper. And if you see, if you want to put this in entire pipeline, so you will have your data and you will create this, self-supervised or unsupervised method here, rotation, and you learn, good representation. And this representation is then, transferred to your actual task, or you can transfer to other tasks as well. So let's see. And this paper, again, this RotNet paper was also used in this paper, semi-supervised learning with scarce annotation, which came from Oxford. And there in their semi-supervised learning paper, for doing the pre-training in the preparatory phase, they use RotNet. And then this pre-trained model was then used in the semi-supervised setting, and they were able to learn good results with just using 10 labels per sample. So, yeah. And this is again a snippet from the paper where this is the image and you rotate it by the 4 degrees 0, 90, 180, 270, and you task the network to predict its degree of rotation. That's just a four-way classification model. Now the authors have put in the paper also the reasons of why they think the image rotation is a good geometric transformation rather than using other geometric transformation. So the first reason is the absence of low-level visual artifacts. So when you rotate an image, simply by 0, 90, 180, 270, there are no visual artifacts that are visible in that because you're just simply rotating it. In contrast, if you do other geometric transformation, like you scale it, you resize it, or you change its aspect ratio, so in order to do that, you will see some kind of, visual artifacts that is built up in the image. So this is one reason the authors have given, and it totally makes sense. Another is well posedness. So usually, when human capture image, they whatever objects that we have, they are depicted in an upstanding manner, vertical manner. So when you're rotating it, by say a 90, 180 or 270, there is no ambiguity about the rotation because in essence all the objects are upstanding, and even it becomes easier for the network to figure it out the degree of rotation, and the task becomes easier. In contrast, had it we'd be using scaling, resizing, it would have been tough because while capturing image, there are human capture image in varying scale, and those are tough to discriminate. And the third reason is, implementing image rotation were very easy. So you can just use just two operation, flip and transpose. So for example, you want to do a 90-degree rotation, you first transpose the image and then flip it vertically. So these are the three reasons that the authors have given in the paper. Then, does it work? Does this simple method, of rotating helps the model to learn good features? And yes, it does. And it's proven from the attention map here. So they say that in order to force the network to learn the rotation, the model is able to learn good features. And the reason is, if a model has to predict the degree of rotation, it should know about the semantics of the objects. It should know about the orientation of the object. That if the eyes are here, it means it's a 0 degree. If the eyes are, vertical, it means 90 degree. So in order to solve that, predict that orientation or rotation, it should know where the eyes are, where the, nose are, where the heads or tails are. And it's evident from the figure here. So on the left side, this is the attention map with the supervised model, where they plot where the model should be looking while predicting the output. And on the right side, it's on the self-supervised model of rotation net, and we can see that the model is in fact looking at the salient features of the images while doing this rotation prediction task. So it proves that they are able to learn good features. And another image the authors have put in is this of the filters. This is with the supervised learning, and this is with the self-supervised learning. And this is the filters from the first layer coming from the LXNet model. And we can clearly see that, on the right side, there are filters of varying orientations and frequency. They're much richer, even compared to the supervised way. And another attention map is with the degree of rotation. So the authors say that, the features learned are, equivariant with respect to rotation. So no matter, uh, it's a 0 degree, 90 degree, 180 or 270 degree rotation, they're still able to, focus on the salient feature of the object. As you can see, the eyes and then the whiskers, etc. So it also proves that they're actually focusing on a good features of the object and not learning some noise in order to predict this rotation. So it does work, it says that. And let's see quantitatively what experimentation they have done to prove their paper works, or I mean their method works. So they have done two sets of experimentation, one on the Cifar to validate different features of the rotation net with respect to the hierarchy of the feature, the number of degree of rotation, what is the correlation, and that other is to show that their model is able to transfer well to other tasks. So let's first see the Cifar case, the Cifar-10 experimentation case. So it's a Cifar-10 experiment. Let's see the implementation details. So basically, the model that you train using rotation net in a unsupervised or self-supervised way, you can call it as a ROTNet model. And here the authors have used this network in network architecture. So what's the difference between, what is it actually? So if you see in this picture on the left is a normal linear convolution layer where we have a local receptive field, and we do a conv operation and which is mapped to an output in the feature map. Whereas in network architecture, there will be net usually it's a multi-layer perceptron that is in between the local receptive field and the output. So the output of conv layer passes through this MLP, and then it goes and mapped to a output in the feature map. So that's the difference, and authors have used this network in network architecture. And this is the training details. They use SGD with batch size 128, learning rate 0.1, and they trained for 100 epochs, dropping the learning rate by a factor of 5 after 30, 60, and 80 epochs. And they have trained the network by using all the four rotations simultaneously rather than randomly sampling any of the rotations. So at each of the training batch, the network will see 4 times more images than the batch size, because each image will have four rotation: 0, 90, 180, and 270. Now, so usually the architecture consists of conv blocks, and each conv blocks has three conv layers. So in most of the experimentation, they have used this one, four con block architecture, where each con block has three con layers and they are network in network architecture. But in order to check how many con layers are better, they've experimented with three con block architecture, four con block architecture, and five con block architecture. And in essence, there will be 9, 12, and 15 convolution layers. So after experimentation, they found that, usually what happens that af the features which are learned uh, after the con block 2 and a classification layer which is trained on this feature after the con block 2, they tend to perform better. And the reason is the learning, hierarchical learning in deep learning. So what happens that the later layer, the features that are learned in the later layer, they are more related to the task that is being performed, and in this case, rotation. And the initial layer, they are more generic features. So if you see this image, I think you'd have known. So initial layer, they have low-level features, then mid-level features, then high-level features, and the later, deeper layers, they'll be more, the features will be more related to the task, and that's the reason that the later layers were doing bad. And another thing was that was observed is uh, when you increase the total depth of the RoadNet model by increasing the number of con blocks, the performance of the object recognition improved by using the features of this. And the reason again being the same that if you have more con layers, then this earlier con layers they tend to have more generic features and not specific to the rotation task. And that's why you can see this the con B3 was close to the classifier layer, and that's why it's doing bad. And this is not close to the classifier layer, it is more of learning generic feature, and that's why it's doing good. And later in this paper you will see that for most of the experimentation the authors have used the features obtained after the conv b2 or the second conv block layer, and on top of that then they have added linear of conv layer and the fine tuning or transfer learning, whatever they want. Okay. Yeah, and then another was exploring the quality of learned features with respect to number of recognized rotation. So you'd be wondering why they choose only these four rotations. Well, they experimented with other rotations as well, and they found that these four rotation tend to work the best. So they experimented with eight rotations by including multiple of 45 degrees, and then they did with two rotations like 0 and 180 and 90 and 270. And why this eight rotation did not work well? Because in eight rotation, if you can see 0, 45, 90, the distinction is less as compared to the four rotation. So it's very easy to classify 0 and 90 as compared to 0 and 45. And that could be the reason that 8 class did not perform so well compared to the fourth class. Not much, but yeah, 1%, a half percent to be precise. And then the two orientation case also did not perform well, a reason being that there were very few classes, that is the number of supervisory signal were really less. And among these two classes, the authors found that using 0 and 180 degrees better than 90 and 270. And the reason is if we are using 90 and 270 and then this pre-trained feature is then transferred to do the recognition task, there it does not work well because the natural images are basically 0 degree, which in the object recognition task, which the model has not seen. And that's the reason that using 0 and 180 is better than using 90 and 270 if you have to go with two rotations. So yeah, this is one more statement from this experiment. And then they did experiment to compare the performance of the RotNet pre-trained model against supervised and other unsupervised method. So this is the RotNet model consisting of four con blocks that we discussed. Now, what they do is they, as I discussed, the features after the second con block were better. So they took this two layer of the RotNet pre-trained model, they freeze it, and in top of they added this conv and linear layer, and they call it RotNet plus conv. And similarly, they have this RotNet plus non-linear, where instead of conv they use three fully connected layer. And then there was a random initialization layer where it's similar to the RotNet plus conv, but instead of freezing the RotNet pre-trained weight, they have frozen some random weights. And this is the supervised network in network architecture, which is similar to this, but just that it's trained in a supervised way. And that's why its performance is highest. Now you can clearly see that using RotNet pre-training and adding a non-linear layer and doing the classification, the performance was 89, and using conv it was 91. And then when they fine tune means fine tuning the entire architecture, the performance obviously improved. and it was even close to the supervised learning. And comparing it to other unsupervised or self-supervised approach, the method of RotNet is far more better, as we can clearly see. And this is for the Cifar-10 task. So this was a comparison which proves RotNet works fine. And this another comparison to show the correlation, how the object classification improves if the rotation prediction task improves. So you know so this red line is the supervised one, so leave it. And this yellow line is the performance of the object recognition accuracy, and this one is the rotation prediction accuracy. So as you can see, as the epoch goes by and the model improves its performance on rotation tasks, then the features are learned in a good way, and even the object recognition task starts to get improved. And another performance was with the number of training examples, and this yellow line is the supervised one. Oh, sorry, the yellow line is the semi-supervised one. I mean, using RotNet based pre-training, and then this one is the supervised one. And you can see with less number of training examples, the semi-supervised or the RotNet based pre-training did a much better task compared to even supervised. So in semi-supervised setting, this kind of method works well. And even in that paper, scarce annotation for semi-supervised learning, we saw they use RotNet and they could achieve good result. Yes, and I discussed in the I think previous to previous video what is the approach of doing evaluation for the self-supervised model. So one is the linear separation where you have your pre-trained model, and then you add a linear layer, and then you evaluate your data, evaluate your results on the ImageNet data set. And then another is using a portion of the data set, like how your model is performing with 10% label data or 20% label data and so on. And another method is obviously the transfer learning, where you use the learned representation that you have learned in the unsupervised way and transfer it to other tasks, for example, detection, segmentation, or other data set, and see how it performs. And that's what the authors have done in this case also. Now that the previous results were with Cifar-10, showing the different efficiency and performance of the RotNet based pre-training. Now this experiment is to evaluate this model on the ImageNet dataset. So the authors have done self-supervised training on ImageNet training dataset, and then they evaluate these learned features on various tasks like classification tasks, which they have done on ImageNet, places, Pascal VOC, detection tasks that they have done on Pascal VOC, and segmentation tasks that they have done on Pascal VOC. And here, for doing the training, they have not used the previous network-in-network architecture. They have used the LXNet with batch norm, and they did not use the LRN. Then they use the SGD with batch size this, and they train it for 30 epochs. And again, they drop the learning rate by a factor. And as in the Cifar-10 experiment, they too also use all the four rotated copies of the image simultaneously, same as in the Cifar-10, all the 0, 90, 180, and 270. Now the LXNet, just to a refresher, it looks like this with five conv layers and three fully connected layers. And to remind you of how so suppose this is your LXNet, you do a pre-training, and then you take this pre-trained model like this, it's a frozen one, and top of it you add your linear or other layer that you want, non-linear layer that you want to do to evaluate it. Okay, and let's see the comparison of the performance of this ImageNet based RotNet based pre-training on ImageNet dataset and how it does with the non-linear layers and the linear layers. Okay, so this is with the ImageNet labels, and this is the other unsupervised metal, and this is with the random initialization. And as you can see, with the compared to the self-supervised method, this is doing okay, not bad, but compared to other self-supervised method and compared to random initialization, this is doing really well. And then coming to the linear classification with the linear layers, which everybody does now, here also we can see that when the uh, the linear classification was done, features from different conv layer of the LXNet, we can see that the performance improved over different conv layers. And compared to the supervised, again, it's not doing that great, but compared to other unsupervised methods like context encoder colorization, jigsaw puzzle, big GAN, it's doing pretty well. Now let's see. So one thing is this is 2018 paper and the model used is AlexNet. So as of now, the state of the art self-supervised model like SimCLR, BYOL or SWAP, they have achieved performance very close to the supervised method, like 80% in here, 79%. And now the basic model that people use nowadays is the ResNet 50. And again, they use a widening factor, more filters and deeper layers. But ResNet 50 is kind of a base network that people use, and they do a linear evaluation, and they have achieved, really 80, nearly 80%, which is, much, much more than this. But this is a 2018 paper, and these are all this year paper, like 2020 paper. So, and they also then transfer this, knowledge that they obtained through this unsupervised training to another task of classification with places 205 dataset. And again, it was observed that, for Con 5, the RotNet is doing better. For others, okay, counting method was doing better, but nonetheless, it was okay. It was not doing bad. And then on the Pascal VOC dataset, if you see, on Pascal VOC 2007, they perform the classification and detection task, and Pascal VOC 2012, they do the segmentation task. And we can see here, so they have sorry here, they have done in classification two computation. So one is using the pre-trained model after the Con 5, and another is fine-tuning all the layers. Okay, after the taking the pre-trained layer, adding their layers, and then doing the fine-tuning of entire layer. So here again, compared to the supervised phase, here 70%, 79, it's 72. But compared to the various other unsupervised method, it is again winning. And in the detection, it is just 2% less than the supervised model. And that time, this was the state of the art in 2018. And segmentation as well, it did better than other unsupervised method, but not compared to supervised. But still, it is something that will give you a boost up rather than doing this random initialization. So yeah, this was the paper and this were the results that I discussed. And to quickly conclude it, they propose a very novel and simple self-supervised task of doing the rotation and doing a four-way classification task. And in this quest, the model tend to learn good feature because in order to solve the rotation task, they have to learn the salient features, the orientations of the images, and they learn very good semantic features, sorry, and which we can easily translate it to other tasks as we saw, like object recognition, object detection, and object segmentation. And then for the model, they use network in network architecture, like this, the con block and the LXNet architecture. And on the data set for the Cifar, they used this network in network architecture and they evaluated the performance. And with AlexNet, they did a pre-training with ImageNet and they evaluated on ImageNet, Places, and Pascal. And the performance was quite competitive with the supervised and much, much better than the other unsupervised method existing at that time. So I think that's all for now. But yeah, they have the code implemented, which I'll also share in the description. So if you want, you can just go and try it, this official GitHub repo. And in the next episode or in the next video, anyhow, I'm going to implement a rotation net on ResNet 18 for a custom dataset, and we'll see how it helps us. So yeah, tune in for the next episode for the implementation of RotNet. Till then, keep learning, keep exploring neurons, and be safe. Thank you.